So good morning and a warm welcome to Bioprocess Engineering today. Introduction lab course, reactor operation. Here we go. So it's reactor operation in a nutshell. We will have a more detailed lecture on that. And by the way, these lectures are already on YouTube, so maybe you have already seen that. So we talk in a nutshell what reactor operation means in order that you know what you're actually doing in the lab course. And the camera has already lost me after 1 minute. So here we go. What we want to see is how this reactor operation stuff works, and then we look at stirred tank reactors, of course, and we look at the batch, fed batch, and the continuously stirred tank reactor, because that's what we also do in the lab course. And this should give you the theoretical background. Okay, here we go. So in principle, we have 3 operation modes of continuously stirred tank reactors. We have the closed mode, the partial open mode, and the fed batch mode. Of course, this is also, again, a high-end animation. So you have already realized that. Maybe this was not 4 hours work, but half an hour. Okay, so the closed mode, the feature of the closed mode is that you obviously fill it, close everything, run it, and that's it. Now my question to you, is that correct? Is a closed mode completely closed, or is there anything going in? Today we do it like this, that if you talk, you get this back and you talk into this back. Whether it works, we will see. And the people in WebEx, they will realize that it makes some noise when I throw it, but that's like it is. So we try. First, I need to wait until she sees the sound. Otherwise, we will have a problem with her head. Yeah, perfect.
All right. I just have an assumption. I'm not entirely sure, but I think gas is still able to enter. We still have a gas inlet and outlet.
So you say what again?
That we still have a gas inlet and outlet.
Gas, exactly. So the gas in-out we still have, and therefore it's not completely closed. But we don't care about gas. So if we talk about close or open, we just talk about, at the end, we just talk about the liquid phase. So you can throw the back, otherwise we have all things recorded again. Okay, so now the volume obviously is constant, but if we operate a reactor, and this is important, we want to produce something, we don't operate it once. Yeah?
I just wanted to say we also introduce energy into the system.
Yeah, okay, energy is also going into the system, that's clear. But again, if we talk about liquid stream, this is what we talk about. But obviously gas and energy usually is going in. We don't use adiabatic processes usually in bioprocess engineering. Okay, so, but if we want to produce something, and this is what we talk about at the end, you want to produce a product, you want to produce a drug, you want to produce whatsoever, you don't buy a bioreactor, run this bioreactor once a year, and for the remaining part of the year you do nothing. You repeat it. Yeah? So you produce once, as you see here, then you produce again and again and again. Now, why is that not directly put together, this production times here? Why don't you produce the second batch immediately after the first batch?
You have to clean it first.
Yeah, exactly. You have to clean it, and in principle, you also have to fill it. Yeah, so you have to clean it, you have to sterilize it, you have to fill it, and this takes, of course, time. So in a closed batch reactor, in between there is no production. And you will see when we talk about and compare reactor productivity, that makes a huge difference. Yeah. Okay, so now we come to a partial open reactor. In this case, it's a fed batch reactor, so this means that we can add something, but we don't take something out. Add something means add medium, but we don't take something out. In this case, of course, the volume is not constant, that's clear. And how you add this depends on you. You can add it in a time-dependent manner, so like kind of an exponential trajectory. You can add it constantly, you can put an intermittent addition and so on, so it's completely up to you. The advantage is that you can produce, for example, more biomass because you can start, as an example, with a higher substrate concentration at the beginning. So this is an example. However, it's still a batch, so you will have to stop it after some time, clean it, and sterilize it, and then go again. Now, how you do that again, also you don't need to completely empty it, you can partially empty it and so on, which is rarely done, but in principle you have every opportunity you want to do. And now finally we come to the open configuration, and this is now our chemostat operation. The chemostat operation is a special operation, and my question is, there in an open configuration, is the volume constant? So you pump something in and pump something out. Who says, yes, the volume is constant, we make a vote? A lot of hands go up. Who says no? Is there a decision in the internet? What do you say? Do you think it's constant or it's not constant? Here the vast majority says constant. Does the internet support this?
Yes, I support it.
You support it. Okay, you are the internet. Okay, that's cool. You support it. Yeah, but I say, who says I can pump more in than out?
Yeah, I say it depends on how much you pump in and pump out. If you pump in more than you pump out, then it's going up. But if you pump more out than in, then it's decreasing.
Yeah, it's going down. But does that make sense to pump more in and out in such a? It makes no sense. But it can be. This is important. You already, if you lifted your hands because you're geniuses, huh? We don't vote whether you're geniuses or not. I say you're geniuses by definition because you already thought, well, it makes no sense to pump more out or in because then your reactor will be full. You cannot run it indefinitely. So the most, let's say, meaningful operation mode is certainly if you pump the same in and out. And then you have a constant volume. And this is the chemostat operation. But you don't need to do that. And this is also important if we do that in the lab course and we have a chemostat running and we don't adjust our pumps correctly, you could also end up with an empty reactor the next day or with a completely full reactor the next day. Yeah? Because the reactor doesn't know what you plan to do.
Yeah, so for me, all of those tank reactors are very similar. Is there like in industry one that's very dominant or one that's sticking out or something?
Oh, I forgot to throw the bag, but this is the risky distance here. It's very similar. So the reactor itself, it's the same even. So you have no difference in the reactor. Again, it's an operation mode. So therefore, thank you for the question. It's just an operation mode. It's the same reactor. You operate it differently. Yeah. So that's no difference in the reactor. Okay. So we do a chemostat and then we keep the volume constant. You will see then later on we talk about the dilution rate. So we will define that then in a second. And of course, in the case of the chemostat, what you do here is you can run that chemostat over quite a long period of time without needing to add to clean in between and so on. So that is the advantage of the chemostat. As soon as there is a steady state, we will see that later on, then you can run it forever. Do you know any examples of bioreactors or bioprocesses which typically run in this mode and which is very common, and I would say each city has such a chemostat in operation?
Some kind of waste treatment.
Waste treatment for what?
For wastewater.
Wastewater. A wastewater treatment plant is typically run, it's typically a chemostat. Yeah, you continuously put something in and you continuously pick something out. This is what a how a wastewater treatment plant is operated. So this is a chemostat. Yeah. So you have it everywhere. So it's not really something which is a kind of a very, let's say, fancy example or so. You have it everywhere. So therefore also chemostat operations are important. So these are the operation modes. And now if we want to calculate an ideal reactor, this is our starting point here. Oh, this animation just went for 5 seconds, so I have to repeat it. It was animated. Okay. So in this case, of course, it's again very simple. So we use our mass balances, what we usually do. So if we look at how we can set up this mass balance, it's clear that the change, I'm just looking where I am, the change of my mass versus time is, of course, so this is my mass balance I always do. It's just, of course, in this case, a mass balance which is an unsteady, so which is not, let's say, fixed. It's varying here. So everything which goes in minus everything which goes out plus everything which is being produced or consumed. It's the same. So then here I have flows going in. So if it's my F in, fold the concentration in, minus my F out, fold my concentration out, plus the production rate, Ri, fold the volume. Yeah? So this is my general mass balance here. Of course, I can have also degradation, but usually, why do I don't put here minus degraded? Because if in a bioprocess, usually I have either degradation or production. So it's fine if I put this term here. And of course, then we have a specific production rate, which can, or consumption rate, which can be either positive or negative. Then it goes in the different direction. Okay, so this is what we have as a balance. And of course, we should also have that on our board. And of course, we can put the little dot here to indicate that these are flow rates. So these are no more constant stuff. Can I change these flow rates during the run of a reactor? Of course. Yeah, so I'm completely free here. So this means that the flow rates and the volumes can be a function of time here. This is something to keep in mind. So we are no more necessarily in the world of a batch bioreactor. But of course, now we feel more comfortable if we go back to the world of our batch bioreactor. And of course, in the world of the batch bioreactor, we had this F in, F out is 0. So we have nothing going in, nothing going out. And you remember what we did here, and this is what we already did in applied microbiology, and what we will do again in kinetics. I will deduce that from the law of Monod. You remember that if we look at the biomass here, that we did the following. Where am I here? Oops. So for batch, F in, F out is equal to 0. Volume is constant. And then for biomass, we could write, you remember that we could say dVx dt this is 0, this is 0, this is 0, is Rx fold V. And we could take out, as the volume is constant in the batch bioreactor, we then could take out the volume here and can write this as V dx dt, and therefore we can kick out the volume, and we had this Rx is equal to mu fold x. We did that more lengthy, that's just in brief to repeat that, and therefore we ended up with dx dt is equal to mu fold x. And if we then solve this differential equation, you remember we ended up with x is equal to x0 e to the power of mu t. So this is what was describing our growth in a batch bioreactor. Now, what can we do that here? So if we look at our a bioprocess, so we want to produce, for example, N concentration of 10 grams per liter, and we start with a starting concentration of 0.1 grams per liter. What are you interested in if you set up a bioprocess? If you want to calculate how much can I produce now per year? I know, for example, in between it takes me 5 hours to clean. Huh? The time, and the time for what? The doubling time, the time it takes to come from 0.1 to 10. So it's not the doubling time, but I want to know how long does the reactor run. Yeah? So that's what I'm interested in. Yeah? The batch time. And of course I can use that equation, I'm simply solving that now. I'm simply solving this equation now to calculate that. So because I can say X final, this is my final concentration, and I say here it's my T batch, and then I can simply solve it. And obviously it's ln x divided by x0, or ln x minus ln x0 is equal to mu fold Tb, or I can say my batch time Tb is equal to 1 divided by mu, max in this case, fold ln x final, I forgot this final, divided by x0. And this equation gives my batch time. Yeah? And then if I know how long does it take to clean in between, then I can calculate how many batches can I produce per year. And if I can produce 10 grams per liter in a volume of 1 meter cube, then I know that I can produce 10,000 grams in 1 meter cube. And then I can just calculate, I can produce X batches per year. In other words, I can produce X kilograms per year. Yes. Sorry? The bags.
T equals 1 over what? What is that?
What T is?
In the box. T equals 1 over something. No idea.
TB.
Huh?
What T is your problem?
Oh, it's
TB.
mu max. Okay. Nothing.
Mu max.
Yes.
Yeah, this is something which is really hard to read. If I wouldn't know that it's mu max, I would also not be able to read it. So it's mu max. But this is very brief, as you know that already. And this is now simply solved to the batch time. Yeah? You also have this formula in your formulary. So you're warmly invited to use the formula. Of course, it's not rocket science to solve that, but if you're, for example, in the exam, or if you do your calculation and so on, you don't want to solve everything or deduce everything all times, because that simply takes time. Yeah? So don't do that. So this is batch. And of course, you can also solve that for, you can also calculate the batch time for how much product is being produced and so on, which we will do that in the real lecture. But at the end, you want to know how long does it take to produce X gram product, or Y gram biomass, or if I have consumed my substrate and so on. And then you just use the rates and so on. You can solve the equation and then you calculate it. Of course, in reality, which is important, in reality, it's not just about exponential phases. So you will see later on, if you produce, for example, a monoclonal antibody or whatsoever, it's not just the exponential growth phase. Usually you also have a production phase where you have a high concentration of your cells. You have no more exponential growth. You have a quasi constant concentration of your cells, but also there they still produce the antibody. And this is then, of course, then also production. Yeah, that's clear.
When a company chooses a specific bacterium for a certain process, is the growth rate one of the key factors they have in mind there?
This is a good question. The question is the growth rate the key factor to use a certain bacteria or not? So this is, by the way, we have an extra lecture in kinetics, which we did not yet have because it is an introduction in reactor operation, and kinetics is of course a prerequisite here. So if I would say normally the biomass is not what you want to have. Yeah? Let's assume it's not the biomass you're interested in. You produce, for example, a metabolite or something like that. Yeah? So is then the growth rate the specific growth rate the only relevant thing?
Well, if we don't excrete our product, it's, the growth rate is actually kind of important, because otherwise it would take quite long to get your final product. If you excrete it, though, it's kind of neglectable.
Exactly. So it kind of depends. Yeah. So it's not easy to respond to this question. It kind of depends. So it's also if the production rate is connected to the growth rate, then in this case, of course, a higher growth rate means a higher production rate. If it's not connected because it's a secondary metabolite, it means that you want to have mainly many cells. Yeah. So this is the important thing here. So it depends. Yeah?
Okay, maybe I'm missing something here, but like if we are producing a metabolite and we have more cells, don't we have more cells that are able to produce our metabolite?
Yeah, but that's the point what I said at the very beginning. You can dissect the growth of your cells and the production. So if the production rate is uncoupled from the growth rate, and this is the prerequisite here, then it's good to have as many cells as possible. So what you can do in this case is, for example, you can design a process that the first phase is optimized for growth, that you have a lot of cells, and the second phase is your production phase. You don't care about growth anymore, but you want to have a lot of cells. Yeah? And you can, of course, calculate that. That's what we will also do in your fed batch experiment. You will do exactly that. You can calculate what makes the most sense, because you will do an aerobic growth where you have a higher growth rate coupled to an anaerobic production of your ethanol. So that's an optimization problem, which is not trivial to respond what is best. Yeah?
Thank you.
Okay. Okay. Okay, so that's easier in seminar rooms, which are smaller, by the way. Good. Now, so we have already said that the total batch time is not just the batch time where we have the growth, but it's also then, let's say, the emptying of the reactor, cleaning, and so on, sterilization. And this takes quite a bit of a time. Yeah? So this cannot be neglected here. Now we come to the fed batch operation mode. Now, if we go to this, I would say we kick away everything here. And now we don't look for the biomass. Let's have a look at the substrate. So, of course, the same equation here is true. Our F out in this case is for fed batch. F out is, of course, 0. And the volume is not constant. That's very important. So I cannot assume now that I have a constant volume anymore. Yeah? So if I now look at the substrate, I have, in this case, I have, of course, a substrate consumption. And what we know from kinetics is that the rate Rs for a substrate is then minus the specific substrate consumption rate fold x. This we will talk about in kinetics, just believe me, but you see that it's the same as by our other equation for biomass. It's the specific growth rate fold the biomass, positive because it's increasing. Here it's minus the specific substrate consumption rate, fold the biomass. Remember, Qs can be a function of time and so on, yeah? Not necessarily constant. So also the specific growth rate can be a function of time, but we say in a batch process, it is not, yeah? So that's important. If you want to solve then at the end the differential equations, then you need to know whether it's constant and you can integrate it or not. What? Next to? To the V. To the volume, it's not equal to. During the drawing, I thought I make the symbol differently, which was not very good for the symbol. Okay, maybe now it looks more than an unequal. Okay, now, okay, so let's put here our differential equation for our substrate. And the substrate concentration is the small s. So I have dV fold S dt is equal to F fold S in. So that's the substrate concentration in the in stream. Plus, minus, put directly this equation here, minus Qs fold X. Yeah? So that's the, this is our differential equation for the substrate in a fed batch process. Yeah? So, here I can throw. This is a short distance process. I'm expert.
So in here in the formula sheet, D is the same as F. So F is the flow. Right?
D and F are different. We will talk about F and D in a second. Yeah.
Okay.
We will talk about F and D in a second. Yeah. So you already know the others, the experts already have their formula sheet next to them, and it's good always check whether the professor doesn't tell bullshit. Usually because if you're at the board, it's like it is, yeah? You write down, and after 2 hours you realize, oh, that's wrong. And then it's always good if you have some checking also of the students. Okay, we'll come to that in a second, yeah? So now, we said dVs dt, so now the volume is not constant. So we cannot pick out this simply from this differential. But what we can do is, you have learned in math, I can write this as V fold ds dt plus S fold dV dt is equal to F fold S in minus Qs fold X. Of course, this is the F in. We just have the F in here. Yeah? So this is how I can write it. And if I look at this dV dt, this is, what is dV dt? The change of the volume over time. Sorry?
No, it's dt, it's the change of volume over time.
Yeah, it's the change of the volume over time. Yeah? Yeah, it's F at the end. Yeah, it's my flow rate. It's F is the change of the volume over time. This is cool. So I can say dV dt is equal to F. So I can simply, you write that of course better in a new line, but I have not enough space. So I can put that as S, the substrate concentration, fold F, the substrate concentration of course in the reactor. This is the substrate concentration of the inflow. And this is a question.
Yes, the mathematical one. Why were we able to pull out the volume out of the integral?
This is mathematical rules. I'm not the one who discovered them. Huh? This is what you learn in math, that you can write this differential here like this. Huh? We all have to believe that. Yeah? Intelligent mathematicians have told us you are allowed to do that. And this is, believe me, don't ask a mathematician why. Hint. He will be happy to explain it to you. But your weekend is gone. Okay, so dV dt is f. This is cool. So we can put that here. And if we now, oh, I forgot something. I forgot something. Here I forgot the volume, of course. Yeah. So fold V. This was here, and I forgot it here. So just add it. Yeah. Of course, it's here. It's a concentration and a specific rate. I of course have to multiply it with the volume because I talk about masses. Now, if I divide here by V, I can kick out my V here. I can kick out my V here, and then I end up with V divided by F divided by V, and now I come to my dilution rate. Now I just define D is equal F divided by V. So this is my dilution rate, and this of course makes sense. This means if I pump in 2 liters per hour into a bioreactor, is that a lot or not? It depends on the size of the bioreactor, exactly. So if I have a huge bioreactor, 2 liters will not be very much, but if I have a lab scale bioreactor which has 3 liters, 2 liters are a lot. So this is, it makes sense to put that in relation to the volume of the bioreactor. And this is exactly my dilution rate. So that's the rate how I dilute everything. So if this is 1, this means per time unit, I pump in the same volume as my bioreactor has. For example, if it has 1 liter, if my rate is 1 liter per hour, 1 is not so genius because 1 divided by 1 is 1. So if I have 2 liters, my bioreactor is 2 liters, I pump in 2 liters per hour, I get out a dilution rate of, just doing the calculation, example, D, no, of course not D, V is equal to 2 liters, F is 2 liters per hour, D is, it's still there, yeah. D is
1.
Almost
1 hour.
1 per hour. That's important. The unit here is important. D is 1 per hour. Yeah.
It's written S is for substrate. Do you mean S is concentration or what?
As the small, it's always the same as for the biomass. For biomass, you write X. Small means concentration, large means mass. And the same for the substrate. Small s is the concentration. So the substrate concentration is small s. Product and product concentration is small p. Large P is the overall quantity of the product. Yeah?
What is the difference between S and S in?
What is the difference between S and S in? There, a good idea is to start with this equation here, because this there you can still see it comes from the first differential equation. So our S in is our substrate concentration in the inflow, and our S is our substrate concentration in our bioreactor, which is of course not the same. Yeah? Because if I have a substrate concentration extreme 0 in our bioreactor, and I drop just a little bit of a very high substrate concentration in, the substrate concentration which I will have at the end in the bioreactor will of course be different.
But it's a small s, so it's concentration.
It's always concentration, yeah. So now I can put that in this equation. I can write ds dt plus S fold D is equal to Sin fold D minus QSX. Yeah? So, and now I can, of course, just rearrange that, and I can say ds dt, the change of the substrate concentration over time is equal to, I just put that D out now, I can say it's Sin minus S fold D minus QSX. So this equation gives the change of the substrate concentration in the fed batch bioreactor. I didn't integrate here. Yeah? So this is just an equation, no assumptions, so that's always correct. So you can use that equation already for experimental calculation of your biomass concentration. Yeah? If you want to calculate your QS, your specific substrate consumption rate, you can use that equation. You can measure experimental values, and then you can say the SDT is approximately delta S delta T. So you just measure your substrate concentration at different time points, solve this equation to QS, and that's it. This is very important to keep that in mind. You can use these equations for analyzing your experimental data. Far distance, no back throw.
That's all right. But this depends on the steady state, right?
There is no steady state here. Here we didn't do any assumptions at that point.
The substrate consumption rate, isn't it dependent on the steady state then? Because we didn't make any assumptions up to now. QS can be a function of time, substrate concentration can be a function of time, even Sin could be a function of time, volume is a function of time, F can be a function of time. We didn't integrate it, we didn't solve it. So up to now, no assumptions. Yeah? Of course, if we want to start to solve it, we need assumptions in order to be able to solve it. But at present, we didn't do anything. And this is important. If you just look at your experimental data, you can, just by putting in your substrate concentration at time point 1 and time point 2, you can simply calculate the instantaneous, for example, the specific substrate consumption rate at that given time point. Yeah? Just by putting in the experimental values. In the final exam, will there also be a few questions or assumptions? In the exam, in the end, you also ask questions about assumptions? Maybe.
Could be. You never know.
They would be good questions.
That would be good. Yeah, that's always, like, you can always hand me in a list of good questions and I will see, not during the exam, before the exam. And so this could be that this is a more general question. Usually, of course, for the exam, again, to this question with respect to the exam, in the exam, you only write what you're asked to do. So if I don't ask you for giving assumptions, don't write 100 assumptions down, because this takes time. In reality, of course, you know it's important. That's always the difference between exam and real life. Huh? Okay. Today I always have my hands down, so why is the camera losing me? Yeah. Okay, now what we're interested in is, of course, we can run this fed batch bioreactor with different operation modes. Yeah? So we could vary at the end. The variation, what we do is the variation of the flow rate. So for example, we could put in an exponential trajectory. We could calculate, if we know the specific growth rate, for example, if we would solve this for the biomass. Now we solved that for the substrate. We can do the same for the biomass. We could calculate, now what is, how do we have to adjust the trajectory of our flow rate in order that the substrate concentration, for example, stays constant, as an example. And then we can solve it and we can calculate F. The most easy thing is, of course, if you have a constant feed rate. So you have always the same feed rate, which is, of course, then meaning that at the beginning, when you have a low amount of cells, for example, you might have a bit higher substrate concentration than at the end. But it's reasonable to say that it's small, and it's reasonable to say, depending on what you do, it's rather constant. So if we say, I want to know what is a good starting point as a flow rate, if I want to achieve a constant growth, so no substrate limited growth, but an exponential growth, and I want to feed in something, you could say, what is a feed rate which makes sense? This is something if we do, for example, if you do your bioreactor, if you do your culture, and you have a biomass concentration, and you want at the end your microorganisms to consume a substrate concentration of 150 grams per liter. Could you start right away with that if you start with 150 grams per liter glucose? What do you think? It's soluble, so you can solve 150 grams per liter glucose. What will be the problem for most microorganisms?
Because in the beginning you don't have enough microorganisms to use up all the substrate?
Yeah, but this is always the same. This is the problem of your batch culture, that you start with a small concentration. What happens with most microorganisms if they see a concentration of 150 grams per liter glucose? You will kill them. Exactly, it's too high. This is how you conserve your food. Yeah? So you cannot start with such a high concentration. So this is one of the potential uses of a fed batch bioreactor. You start with a lower concentration, first run an initial culture until you achieve a certain biomass concentration, and then you start feeding in a highly concentrated glucose solution, for example 150 grams per liter, and then you can of course achieve way higher biomass concentrations than you could achieve if you have to start with a lower concentration at the beginning. Yeah? So that's an intention here. So what we could do is, if I want to do that, I say, of course, I have to start with a certain batch culture. So I start with a certain volume, with a certain concentration in batch. And then at the end, for example, I have, or this batch culture is 5 liters, for example. And then I can fill this up to 10 liters. So I go from 5 liters then to 10 liters in my fed batch phase. I know that on average I will have 7.5 liters because I'm doing a constant feed. I can easily calculate that. And I want to know now, how is my feed rate? What is my optimal feed rate in this case? Yeah? And this I can deduce now from this equation. If I make a couple of assumptions, I say, well, the substrate concentration in my culture itself will be, I would say, quite small, and I assume it's almost constant in relation to the other things. So I simply assume the SDT is 0. This is an assumption for this first approximation what to use. I say F is what I want to look at. V is equal to the V average. So this is what I just calculated. If I have 5 liters batch culture volume and at the end I have 10 liters, then my V average is 7.5 liters. Yeah, very simple. Of course you can put a formula, but I don't want to waste my space here with putting formulas. And then I say, okay, my biomass concentration, does it change during such a fed batch phase? I have at the same time a dilution, but I have a growth. I would say, yes, it will change, but I can say, okay, I approximate that with an average biomass concentration. Yeah. Of course, that's not absolutely correct, but it's a first estimation. So in this case, it's better than nothing. You always have to think of what you want to do. Yeah. You can, of course, think of mathematically calculating everything exactly. But we're in the experimental, in the real world. It makes no sense to end up with a mathematical correct solution with 20 digits behind the commas, but it's useless because the reality is so far away.
Yeah, so like that's my question. Why do we make this assumption?
Why do we make this assumption? / why do we do this calculation at all? Because our intention is we want to estimate a feed rate. A feed rate which makes sense in our system, and the feed rate is for example, the feed rate if you want to optimize your ethanol production for yeasts with glucose, and this is what you will do in your simulation experiments. Yeah? So this is what our starting point is.
So we only refer to like the beginning basically, and only calculate all the beginning stuff.
Exactly.
That's why we can make this assumption.
Exactly. So we need to have a value to start with. Yeah? So, and then we go with the experiment. So this is a different thinking. So math is fine, but at the end, we need to see whether things are going like this in reality. So we will have to do an experiment. But we don't want to start with a feed rate, which is completely useless. Huh? So therefore, we start with a feed rate, which we deduce with a couple of assumptions. This is my back distance, so therefore I can throw my back.
So because we're looking for the initial concentration, then that's why it equals 0 as ds over dt.
The SDT, the change is 0. The substrate concentration is of course not 0, but the change of the substrate concentration is 0.
But always for the F initial, then it would be 0. Or what? Because we're looking for the initial feed rate, right? F.
This feed rate is, we talk about constant feed rates here.
Oh.
So we don't want to change the feed rate, so we want to keep a constant, the feed rate constant.
And
of
then,
course, if we would use an exponential trajectory and so on, this is not the approach. So we talk of a setting where we use a constant feed rate, and we just want to bring in a high concentration of our substrate, and we want to optimize for example, ethanol production.
so it would always be the case that V is V average and ds over dt is 0 for this constant.
This setting, it's the case. It's always we make our life easier, yeah? Because we're not Frank Platte. Frank Platte, of course, is someone who he will calculate everything, but we're too stupid. So therefore, we have to do some assumptions. But we sleep well. This is the cool thing about that. Yeah? I think I don't have to tell students that they sleep well. So, okay. Now, so we're here. We say that V is V average, and we say that X is also X average, which is also, of course, an approximation because we know that the biomass concentration is also changing over time. The volume is changing over time, but we don't want to make things too complicated here. And therefore, we just put that as a linear change, and we don't care too much about the real trajectory. So for an approximation, that's fine. So we put everything in this equation. So we have, so of course, D is then F divided by the average. Is that still there? Yeah, now I have to go a bit down. So we have 0 is equal to S in minus S fold F divided by V average minus QS fold X average. And again, what we want to have is the F, don't forget that. So we simply solve now for the F. So we have F divided by V average is equal to, is that still on the board? Almost. F divided by V average is equal to QS, so we bring that over, and then it's positive, QS X average divided by S in minus S. And then, of course, we just bring over the V average fold V average. So this is our equation. We have deduced from the mass balance how can we estimate a first flow rate for our optimization experiments. I see happy smiles here. or I don't know whether these are happy smiles or whether these not happy smiles. I can't see you smile, you have a mask, but I assumed. So are there...
Sorry, it's a very quick one, you don't need to do it. S_in equals S0, right? S_in is the original,
The S_in it's always constant. It's not S0 because S0 by definition is our starting concentration in our batch culture. So therefore, we don't use S0 here. S_in is in our medium container where we pump everything in. Yeah? And the S is the substrate concentration in the reactor. Yeah? What makes you feel so unhappy?
Me?
No, one behind.
Neither happy nor unhappy.
Neither happy nor unhappy. Just feeling well. Okay.
Before we used assumptions to calculate starting values to get off with. But this flow rate we just calculated, it's based on assumptions, like the average flow rate, or is it like one that holds?
So we want to set up a system where we have one constant flow rate over the complete period of the complete feed time. Yeah. So that was why we did that. If we want to calculate exponential trajectories and so on, this makes no sense. Yeah. This is just for the system where we have a constant flow rate over the complete period, and we want to optimize for that. And we want to have a starting value. Yeah? And this is what you do again in your fed batch experiment. So that's what we do here as a calculation. Yeah? Of course, we can also deduce equations for the biomass and so on. And what I already told you, what could be the aim of such a fed batch process is keeping substrate concentrations low. Again, we will have a lecture on that where we talk a bit more. We don't repeat all this calculation here, but we will talk a bit more about all that. At the same time, we want to keep growth of product formation as high as constant. And of course, if we have a feeding strategy where we have a constant feeding stream, makes our maths easier. The aim is increase the yield at moderate substrate concentrations. And we want to, here we dimensioned the F. Of course, also, we could vary and optimize for the substrate concentration in the inflow. We could optimize for our initial volume of the batch culture. We can optimize our batch time. We can optimize our feed time, and so on. So you see that there are many variables popping up at the end, which makes this optimization problem quite a bit complicated. And you are completely free then in the lab course, in the simulation, what to do. And of course, then the one with the highest ethanol yield will get a prize, yeah, to have an incentive. Now I see happy faces. Yeah? More happy faces. Okay. There is a back question in the front and a non-back question in the back.
That question as well, I think. So this A-looking thing in last formula, is that Q actually?
Sorry, what?
A-looking thing, AS, is that Q or actually S? A.
This is a Q.
Okay, that's Q, nice.
This is specific substrate consumption rate, yeah. Oh, don't throw away my camera, that was it. That doesn't give us additional points.
Yeah, so I wondered if I was a process engineer in industry and I would calculate this there, probably I wouldn't make as many assumptions, or would I? Is it just because we don't know as much? But I don't know, in Germany, we'd say, es fühlt ein bisschen wie Fusch an.
So, as you had no back, I have to translate this question. The question of a potential German process engineer, isn't that Pfusch? I don't know whether there is even an English word for Pfusch. That sounds, what?
Cheating.
Cheating, cheating is not Pfusch. Pfusch is, I think it's really German. This is, so all the non-native speakers learn this word if you're in Germany. Pfusch. Germans don't like Pfusch.
I would have Fush means Bosch. Fush means Bosch in English.
Bosch?
Bosch. B-O-T-C-H.
B-O-T-C-H, Bosch. Never heard. Never. But this is Botch I have never ever heard in English. Sorry? Okay, so push is an important word in Germany. So if you become a process engineer in Germany, learn that word. So this means that, is that something which is, let's say, we should feel comfortable with? Is that something which is really we're allowed to do? And the answer is, you're paid for your time. So of course you could invest 5 weeks of doing a precise calculation. And then you come up with a precise value. You will be happy. And then you will start your experiment and you will realize that your precise calculation was precise, but has nothing to do with reality. So you will go to your boss and say, I have invested now 5 weeks in calculating. I have solved a system of differential equations. I found discrete solutions. I have published the results in Nature Medicine. Not Nature Medicine, most likely not. And what will your boss say? You're fired. I don't pay you for calculating around. I pay you for coming up with solutions. So it's weighing that. Also in Germany, it's weighing that. You weigh the time you invest for the output.
Like it's always done, the person can always get off with it.
That's the point. You as an engineer, your job as an engineer is what simplification is possible and what makes such a big error that your result will be completely useless. And it of course also depends on your setting. Yeah? So this is your job as an engineer. Okay. Push. I will have to talk to a native speaker whether this really is used. We don't want push here. So, okay, now this is also, well, the challenges here. Of course there are challenges, and this maybe is the push slide. If we do some calculations, so also the substrate requirements grow exponentially. This we have neglected. Also the oxygen might become limiting. So the change in metabolism might occur. This concentrated solution might pose problems because we have the formation of inhibitory substrates. And if we want to measure everything in real time, this is also not so easy. Cool thing is, if you are then a process engineer and work in industry, usually they have Raman spectroscopy, so you can trace substrate concentrations in real time. We have also Raman spectroscopy, but unfortunately Frank does not yet develop a cheap Raman sensor for our bioreactor. The solutions are for this Raman spectroscopes for bioreactors are in the range of 150,000 euros. This is too expensive. Yeah? But if you have that, you can measure substrate concentration in real time. This is cool. Yeah? Okay. Now these are the strategies. You see that's not the only one, but what we are talking about is the constant feed strategy. And of course also we use that. And as an example, this is a gas-controlled feeding we used in our system where we feed it in, where we did a biopolymer production. This was a bachelor thesis. And I think this is Chika's data. And she feeded an acid which is toxic and always look for the gas, and as soon as there is a drop of the gas, the pump was programmed to pump then the substrate back in. Yeah? So this means that the feeding strategies can be regulated in a different way. Yeah? So then things start to make sense. And okay, it's technically simple, and this is what we have deduced, and this is the equation which we hopefully have here. And here you have even your S0. Look, in this equation you have no S in, you have your S0. Although I'm not so happy here with this S0, I should substitute it for the S in. Now, if we want to estimate this initial feeding rate, we have to think over a couple of things. So of course, the batch is dependent in the feed medium at the initial concentration. So therefore, that's the real S0. If I have a high S0, high V batches are possible, long feeding times are possible. Usually you say that our batch volume, the volume at the end of the batch, when you start your feed, is around about 0.3 to 0.5 of the maximum volume you can put in your bioreactor. Attention, maximum volume, liquid volume of your bioreactor is not the volume you can put inside a bioreactor. If you have a 30 liter volume, if you put in 30 liters and you gas at the same time, you will come into trouble. So there is also a working volume. So if we talk about this volume in the bioreactor, this is always the working volume of our bioreactor. So the initial S, we can deduce the substrate uptake rate from a batch experiment, QS. So we make a batch experiment, measure QS, and use this QS to put in these values. We can also use an initial experiment with a batch culture to estimate the average biomass concentration. So we just take the biomass concentration at the end of a batch experiment. And the substrate concentration, we also have a problem. What is the substrate concentration in our fed batch process? We have no idea. So what we can do is we use a substrate concentration close at the end of our bioprocess. Usually it's very low. Usually our S in is very high. So if we look at this equation here, it's quite clear that the S in is a very high concentration. And if I have a high concentration of biomass growing in, we are quite sure that this S in the bioreactor will be quite low. So if this is 150 gram and this is 1 grams per liter, whether it's at the end 1 gram per liter or 1.5 gram per liter doesn't make such a difference. So the error is not so high. And this is again the push question. So this is again, we are the ones who need to judge whether this makes a big error or not. It will make a big error if our S in is low and this concentration is high. But this is usually not the case. Yeah? So now I can use again this equation here for the this equation here I can use to analyze the experimental rates. And now this looks absolutely complicated, but it isn't. This is the cool thing. I now have to look back to my almost happy looking people. These usually you look at this formula and feel unhappy because the formulas are so large. But these are really maths 5th class at school, at most. Yeah? So because it's simply, this is the average biomass concentration, just the other way around, 1 divided by the average biomass concentration. And then you have this xi plus 1, xi, it's just the index. This is time point 2 and time point 1. So that's x2 minus x1 divided by t2 minus t1. This is delta x divided by delta t, or ds dt. And then it's exactly this equation which goes here. And then you use it for the biomass. And of course the substrate, this is the one here going for the QS. So you solve it to QS here. And you use, instead of the SDT, you use delta S delta T. And of course for the substrate concentration, you use the average. Yeah? That's it. So there at the end what you do, you put these formulas once into Excel and then you simply copy it down and that's it. Transferring these formulas takes a minute. And make sure that it's correct. Check it a couple of times because the error source is putting these formulas incorrectly. And you never make that. Also, I don't. Initially, there's always an error. So check whether it's reasonable. And then you just copy it down and that's it. Yeah? So this is how you can use that for calculating experimental value. Are these formulas only correct if the volume is approximately constant, QS is constant, our feed rate is constant? Who says yes? Hands up. There are 3 hands. Who says no? Hands up.
So the question is if they always hold, basically.
Yeah, can I use these equations if my feed rate now is not constant, or my volume is not constant, or my biomass is not constant, and so on? You say yes, can you use that? Who says again no, you can't use that? What about the internet? Is there still something there in the internet? Maybe that's the first question. Is there someone in the internet? Oh.
Yes.
This is good. So what would you say? Is it, would you say constant, is it only applicable if it's constant, or is it if it's only applicable if, or can I use that always if I vary the, in reality, biomass and so on varies?
I would say the first option.
So constant, yeah. But the cool thing is, no, we didn't, for this equation here, remember, for this equation here, and this is the equation we use, not, of course not just for the substrate, for our QS, we didn't make any assumptions to come up with this differential equation. If we want to solve this equation, we need to start coming up with assumptions. But for this, we didn't need to do any assumptions. So in other words, in this case, it's valid always. We can use that. Of course, the larger the interval is, that's always our delta. The problem is it's a delta S delta T. If we look at the substrate concentration, it's not ds dt. So the larger the interval is, the more unprecise the value will be if there is a variation. However, we can use that. Yeah? Of course, again, do we get a higher precision if we, in a real world experiment, if we now say, okay, if our delta x is half an hour, Professor Fensterle said, then of course half an hour, that's far away from ds dt. If we look at our equation where we want to calculate qs, yeah? Is it then better to take 5 minutes as an interval?
Better than an hour?
Huh?
Better than what?
Better than half an hour interval? So I said, who says yes, it's better to take a 5 minutes interval?
It should be better to take as little interval as possible.
Yeah, so then 1 minute might be even better.
Yes, 1 second even better.
This is for your lab course. We always want to do the best. So this means that every 1 minute you take samples.
Oh, no, I take
No. You told me.
Oh, no.
I always want the best for you.
Let's stop on 30 minutes. Let's increase to an hour.
Okay. So, but what is the problem? First of all, you don't want to do that in your lab course. But could there be another problem? So, and they all agree. I only see hands up. So, is there another? Could there be another problem?
It's not a problem.
So this, because of this thing at the top, this is only relevant for the lab. We will not need to use these specific equations in the exam because you mentioned.
Okay, because it's only relevant for the lab and not the exam.
No, that's the question. Is it only relevant for the lab?
The little man here, yeah, this is because you don't need to learn these equations somehow. Makes no sense in the exam. So it's experimental value. Yeah. So, but the question was, is it just because I love you so much that I don't want you to take a sample every minute? Or is it because, or is it also, it's better, is it also because it makes no sense to take a sample every minute, even if you could handle a sample every minute?
We don't necessarily need it and it costs money.
It costs money, so that's also, again, the weighing, sampling, analyzing, and so on costs money, one thing. But assume we have money. There were no lab courses the last 2 years, so we have a lot of money left. So we could do sampling every minute.
But also our reactor.
Yeah, Ramona.
Not volume, we take a lot of samples, like the entire reactor.
So maybe you can repeat it. I have.
Yeah, okay. Reactor has not infinite volume, so if we take a lot of samples, we take entire reactor eventually of samples.
So that's an important point. So if you take a sample, of course, the volume of your reactor will go down. So you interfere with your process. So this means that an indefinite amount of sampling, you have just an empty reactor. But there is another point also.
I just wanted to ask, like the sample volume that can be very small, can't we neglect this change in volume?
Yeah, it depends. If we are in a large-scale bioreactor in industry with 20,000 liters, yes. But you will need to take a sample of 1 or 2 milliliters. You need to wash tubings and so on. Yeah? And if we have a 500 milliliter bioreactor and we take a sample every 2 minutes, this adds up. Yeah? But it's about measurement precision. If we do you remember how your CFU values looked like in the method section? This is what you did, I think, also in presence, yeah? The methods in applied microbiology. And your CFU values had error bars of a couple of 100%. So, and all the measurements here are in general so imprecise that you don't gain tons of precision if you take a lot of samples. So you would, of course, still average, if you just look at one value, this is useless. You will average over a couple of values. But it's, let's say, just increasing the interval will not give you much precision. That's the point here, because the measurement is so imprecise. Yeah, volume interfering is an issue. And of course, you're too lazy. This is also an issue. Yeah? So this all comes into play here. Oops. So, and the cool thing is, if you want to take all into account, you use an integral method, and we have a video on analyzing experimental data, how you can do that. You can use, for example, an extrapolation. And now we come to the continuously stirred tank reactor, our chemostat. And we start again with this equation here. Now, what did we say for our chemostat? We said we want to have a constant volume here. So our inflow and our outflow is the same. Otherwise, it makes no sense. So chemostat, F in is equal to F out is equal to F. Of course, we still have D is equal to F divided by our volume. And as F in is equal to F out, our volume here is constant. Yeah? And now we look at for the biomass. Now, before we have looked at the substrate concentration, of course we had the equations for the biomass also in the slides. But here we look now for the biomass. And of course for the biomass we know Rx is equal to mu fold X. This is of course the same as for our batch culture. So if we use that, we can look at this equation. What is our biomass concentration in the inflow in a bioprocess we do here in our bioreactor? What is our biomass concentration in our feed stream? 0 in general. Yeah, it would be rare that we pump in biomass. This is of course not the case in the wastewater treatment plant, for example. Yeah? So this is not always the case, but in our case it is 0. Yeah? So X in is 0. So for our biomass, this term here gets 0 because our biomass concentration is 0. Yeah? So we take out the volume already of the differential because we know that it's constant. We have V dx dt, here we are, is equal to F x in, which is 0, minus F, and our biomass concentration in the outstream is of course our biomass concentration. It's the same biomass concentration as our concentration in the reactor, because we always look at a continuously stirred tank reactor. And of course, we use at optimal we think of optimal conditions where we have an even distribution, which usually is the case. This assumption is quite no push. It's close to reality because we need to put in the gas anyhow. So we will have a rigid agitation in our bioreactor. So we have F fold X. This is what's going out, plus mu fold X fold V. Now we don't forget the volume here. Yeah? So Rx again is mu fold X. So we just put everything in here.
And just for clarification, why is there under the F no index?
Because we have said that F in is equal to F out is equal to F. I always put away this. I know that if you're physics and so on, you would always put this dot for the rate in order to remember that it's a rate. This I omit. We keep that in mind. Yeah. I think it looks more beautiful like that. This is my aesthetic meaning here. So now our X in, this is something we said this is 0. So the complete term gets 0. So it's gone. Yeah. So again, this is optimization of space here because I have just such a small board. Now I'm dividing the volume. And of course, this volume gets kicked out. This volume gets kicked out. And here I have F divided by V, and I have said this is D. Yeah? So if you copy that, it makes sense to make a new line that you see that also. So I have divided by volume, and then F divided by V gets by definition my dilution rate. In other words, how much do I pump in per time in what volume? Again, the unit, remember, is before we have calculated 1 liter per hour in a volume of 1 liter. So my unit of my dilution rate is per hour, or per minute or per second, depending on how you define your rate. So we have dx dt is minus dx plus mu x. And then, of course, I can just, what I do now that it looks more beautiful, I just take out this x here, then I have mu minus d fold x. So this equation, this simple equation, gives my biomass concentration, the change of my biomass concentration in a chemostat. Is that true if my, any assumptions here? No. The only reasonable assumption is that my inflow concentration is 0, which is usually the case. And the volume is constant because I say I'm in a chemostat operation mode, in and out is equal. So this is true in all conditions. Yeah? But in a chemostat, if I want to run the chemostat forever, do I expect that in a steady, so-called steady state, do I expect that there is a change in my biomass concentration? No. If there would be a change in the biomass concentration, it wouldn't be a steady state, because then it would be full at the end or empty. In both cases, it would be not cool. So by definition, in a steady state, my biomass concentration needs to be constant.
Sorry, maybe stupid question, but why is the dilution rate negative?
The dilution rate is not negative. The dilution rate is it's just coming out of this formula here, because it's a mass balance here. Here I start. Yeah, I just put everything in this equation, and the F in is equal to the F out, positive both. But in my mass change, I subtract everything which I pump out. So therefore, this negative comes from this minus F out. This is 0, because my biomass concentration is 0. I can do the same with the substrate. There is, of course, not 0. Yeah? We did that with our fed batch process when we used our substrate. There, it's, of course, not 0. Here it's 0. This is not 0, but it's negative because it decreases my mass. It's not the dilution rate which is negative. It's the mass change, yeah? What I'm looking at. This is back distance. This is
Is it relevant to know how to work backwards from this biomass balance, this final one, mu minus d times x? Will we have to go back and make, break it into bigger, sorry, not break it, but expand it, let's say, back to this initial one?
No, you always go this way down because you know where it went.
Right, so we will need to just use the final one and not need to know that it, back to F times C, etc.
You remember that it comes from the mass balance.
But we'll not have to use it.
You will not need to do that again. Yeah?
Okay.
But you need to remember that it comes from the mass balance. This is important.
Sorry, maybe I misunderstood, but you said that biomass concentration is always constant, right?
Sorry, the biomass?
Biomass concentration is constant.
The change of so dx dt biomass concentration is constant over time in the steady state. Yeah.
So the change in concentration.
There is no change in concentration. This means that the biomass concentration is constant. Yeah.
But why?
Because the point is,
can die or multiply. So
the point is, if we want to run our chemostat forever, it has to be constant. Otherwise, it will not work. If I have a change in my biomass concentration, I cannot run it forever because then at the end it will be full or empty. So it has to be a constant biomass concentration in the steady state, otherwise it will not work. You will do that experimentally in a chemostat.
But how are we ensuring that it's constant?
The bioreactor needs to get at a steady state. So we start it, and if we come again the next week, if it comes by itself to a steady state, then it is constant. If it doesn't achieve that for whatever reason, then it's obviously there was a problem. But then we have our empty bioreactor, for example.
But then, still want to clarify. So then biomass is constant not because nothing is happening, but rather because the same amount of cells is dying as growing, I guess.
Not dying, pumped out.
Oh, pumped out.
Okay. Not dying. So we assume here that it's just growth, which is reasonable in such a case. Yeah.
Okay, got it.
Don't forget, this is important. We are here in a chemostat. We continuously pump something out. So this means that if you grow, you can use that formula again to calculate the specific growth rate. And remember, it's the same as before. We can say dx dt is approximately delta x delta t. And then we can solve this equation to my specific growth rate, and I can calculate the specific growth rate based on that. Yeah? And there is growth, because I have this, even in the steady state, dx dt is 0, but there is growth because I have a dilution. And now comes the coolest thing about this chemostat. Come on, this is important. Don't miss that. Now, if I say in steady state, dx dt is constant or it's 0, so my biomass concentration doesn't change, then I have 0 is equal to mu minus d fold x. And when does this term become 0? This is a very, very simple question. When mu equals d or x is 0. Yeah? So if I have no biomass, there is no change in biomass concentration. This is trivial.
But isn't x always 0?
X, the change, dx dt is 0, but not x. There's, of course, if I have no biomass inside, then it's simple. Then there will be no change in biomass concentration. But if mu equals d, then this term becomes 0. So, and this is the most beautiful formula you have seen today. You're getting more and more happy. At the end, you're again the happiest people in the world for a couple of hours, minutes, seconds. So this means that for achieving that steady state, to be able to do that, and they can do that, these microorganisms have to achieve that themselves. Yeah? They are in this bioreactor, and they have to know what to do in order to come up to the steady state. This only is possible if mu is equal to d. And why do I say that this is so beautiful? What is mu? Is this something technical or this is something biological? This is biological. What is d? Technical. D is something I adjust. So in other words, what I can do is I can adjust in a chemostat growth rates. So I can just by turning around and increasing or decreasing the flow rate of my pump, I can adjust a biological parameter, a specific growth rate. Of course, if I change it, so if I go up to a higher dilution rate, there will be some time until this is no more a steady state then. They have to adapt and they will come up at the next steady state. But as long as I don't change the dilution rate, as soon as I have achieved a steady state, they have to grow with the same specific growth rate like the dilution rate. But now again, the push question, maybe 1 second more, the push question. This can only work if they have the same unit. Isn't it true? So if then I have different units, that would be bizarre. And now I'm a bit afraid because I did a lot of maths here, simple maths, but now we end up with something, my mu is equal to d, and I'm a bit nervous because if my dilution rate has a different unit than my specific growth rate, then I would say, ooh, this is a problem. This would be a real problem. What again was the unit of my dilution rate? Per hour. And what is the unit of a specific growth rate? Also per hour or per time, per minute, per something. So the same unit. So this is also from looking at the unit, correct. So this is really cool that we can set a biological parameter by setting a technical parameter. And this is what you will also do in your lab course. So you will establish, set up your chemostat, run it. You have start, of course, with an unsteady state. The bacteria need time, or the yeast need time to find their steady state. This takes 2 or 3 reactor volumes usually. So this takes overnight. And in the next day, hopefully, we have achieved a steady state. And then you will measure that. And then, of course, we will change the dilution rates. Now, there was a question.
Yes, I'm not quite sure if I'm getting this correctly. You said that we are able to, with adjusting to the dilution rate, the specific growth rate, essentially. But as fast as we do it, we don't have a steady state anymore, right? Like
exactly.
When I adjust the dilution rate, then it doesn't hold.
So exactly, if I change the dilution rate, if I pump in more or less, then it will take a time until they adapt again. Yeah? So that's clear. So we will do that in the experiment, so we can also measure how long it takes. Yeah? This is clear. But if I don't fiddle around with the dilution rate anymore, I will have an indefinite steady state, and I will have an indefinite specific growth rate which equals the dilution rate. Now, can I change the dilution rate to whatever value I want?
Yes.
Technically, yes. It's just if I have a large pump. Huh?
But you can also reduce the volume.
This is I can, but as by definition, by chemostat, I pump the same in as out, so therefore I would not reduce my volume. Technically, yes, but in practice,
I would assume there are still limits to how fast can microorganisms grow. And
so what is the upper limit here in this case? Can you give me a number?
I think it's like the organism basis.
Is there a value you can say what is the upper limit?
The maximum growth rate?
The maximum specific growth rate. Full stop. This is the limit. So because if I would increase the dilution rate further, it's yeast. So yeast will not be able to grow faster than a certain specific maximal specific growth rate. Yeast, for example, the limit is 0.4 per hour. And if I would set a dilution rate of 2 per hour, this is too high. What will happen? I will simply wash out the yeast. So then the other stable steady state will be achieved, x equals 0. This is very stable if no biomass is inside. But this is, of course, not something where your boss will be happy with you. Yeah? So this is the chemostat experiment. And now just having a look on how, of course we can do then the balances also for the substrate and so on. And of course we can also put that to calculate based on the experimental values. And again, also these calculations are just deduced from these equations here. Yeah? So now I'm coming to these two values here. So I have my critical dilution rate. My critical dilution rate is the dilution rate where the end is achieved. Well, I cannot go above mu max. In reality, it's a bit smaller than mu max. Yeah, that's clear. But I cannot go over mu max. And this is the maximum here. This is mu max fold the substrate concentration in my inflow and the Ks. And you see if my Ks is way lower than the substrate concentration in the inflow, which is usually the case, then the critical is more or less mu max. And you will see also the optimal. So this is the dilution rate where I have the highest productivity. The optimal is quite close to this D critical. So in reality, of course, I will not run a bioreactor very close to this D critical if I have no additional alarms and so on, because then there is always the risk that on Monday I have a sterile bioreactor, which makes you not happy. Usually you will check for turbidity and so on. You will have additional measures inside.
Mu max is constant for
mu max is constant mu max is for a substrate and a given organism specific. Of course, you will have to measure that for your certain setting, temperature dependent and so on. Yeah. pH dependent and so on. But of course, you can use tabulated values there. So we are almost done. Almost done.
What was Ks?
Sorry?
Ks, what was it?
Ks comes from mono. So this is what we will talk about if we talk about kinetics. Yeah. So don't worry, this is something we talk about kinetics. So Monod law is mu is equal to mu max fold S divided by Ks plus S, which is the same as Michaelis-Menten. Yeah. And the Ks is this constant, the Monod constant. And usually this Monod constant is way lower than your substrate concentration. And therefore, in reality, we are always close to 1, and therefore we are close to the maximal biomass concentration. But at the end, and this is very important, that's the diagram what we are talking about. At the end, we want to produce as much biomass, for example, as possible. So this means the higher our dilution rate is, the higher our productivity. Because if you solve these equations, you will see that your biomass concentration and your substrate concentration is quite constant over a quite substantial range of dilution rates. This comes if you solve these equations with Monod and so on. We didn't do that. But if you do that, you will come up with these curves here. This means if my biomass concentration is constant, more or less, as a function of dilution rate, if I double my dilution rate, I would produce twice as many cells as with a lower one. So it makes sense to go up. And this is linear almost. Yeah? You see that this is the dx scheme. And if you come up with the optimal dilution rate, then you're in optimal. And if you go further, then of course it rapidly declines to 0. And then you're at the critical dilution rate. So this is this famous dx-d diagram of chemostat. And we will talk more in detail about productivity. So productivity per volume is in a chemostat way higher than in a batch culture. This is what we will then also discuss in the lecture. Now at the end, this is how it will experimentally look like. You see two animations. Do you find the two animations here in the scheme? It's 3 animations, yeah. so this is. I think it's for me. It's just important that you get an idea how the setting look, and there is an additional video how to assemble that. Watch these videos, because one intention also of this experiment is there is a lot of tubing. You will see that there are tons of tubes around, tons of pumps around, and you have to learn how to work sterile in such a setting. Yeah. So that's it for today. That was again reactor operations in a nutshell. We will have an additional look and look at some points in more details, but these are the things which are relevant for the lab course. Thank you very much for your attention, and now I'm so happy to release happy people back to this wonderful day. Looking forward to seeing you, some of you again on Friday and the others next week. Bye.